Hello everyone, in this video we are going to consider flow of a liquid down a solid wall over here. So what we're going to have is some liquid that has some thickness h that's flowing down a wall. It'll have some velocity profile, and our goal is to try to figure out what is that velocity profile. I'll point out that the flow direction is in the x direction and the origin is here at the edge of that fluid, and the y direction goes positively towards this wall. To solve this problem, we have a couple assumptions we're going to make. So first, our assumption is going to be we're going to have unidirectional flow. So that means there's only going to be flow in this x direction. And we're also going to have fully developed flow, which means that that flow is not going to change as we move down in this x direction, and it's also not going to change with time. The third assumption is that the viscous stresses in the gas are negligible. So that means that here we have a liquid that's represented in this white color here. There's also a gas on the outside of that liquid. We're going to assume that any viscous stresses that are going on in the gas are going to be much smaller than the viscous stresses that are going on in the liquid. To solve this problem, we're going to use the Navier-Stokes equations. And I focused on this equation where we have velocity in the x direction. Now in this equation, we can actually cancel out most of these terms. All of these terms will cancel out because we don't have any flow varying with time. We don't have any flow varying in the x direction. Our velocity in the y direction is equal to 0. Our velocity in the z direction is equal to 0. So this whole left half of the equation will cancel out. We'll be left with some dynamic pressure term. And these terms will also cancel out. So after the Navier-Stokes equation, we end up with 0 is equal to negative dp dx plus mu d squared vx dy squared. Before we can start solving this problem, we need to answer two questions. One, what are the boundary conditions? And then also, what is this pressure term right here? First, let's look at the boundary conditions in this problem. So in order to make that a little easier, I'll just redraw our picture over here. So again, we have a solid over here. We have a liquid. And then we have a gas outside of that liquid. So we have two natural boundaries. We have one boundary right at this intersection here between the solid and the liquid. So that is at a value of y is equal to h. And over here, in between the liquid and the gas, we also have another boundary at y is equal to 0. So we'll approach both of these. For y is equal to h, we're going to use a no-slip boundary condition and say that the velocity in the x direction is equal to 0. This is a pretty standard boundary condition in a lot of these problems. We don't have any flow right at that surface of the wall. Y equals 0, we're going to use a no-stress boundary condition. And this goes back to one of the assumptions we made. So I'm just going to jump back to this slide here. We assume that the viscous stresses in the gas are negligible. So that basically means that the gas over here is not applying any force or stress on the liquid as it's moving down, as it's sliding down the solid surface, or at least that viscous stress that the gas is providing is negligible compared to the viscous stresses that are going on within the fluid. So we can represent that by the letter tau, and we can give it subscripts yx. This y refers to the surface that that viscous stress is acting on. So this is perpendicular to, or it's a surface perpendicular to y, and it's acting in the x direction. And in this case, we're going to set that equal to 0. To turn this into something that's more useful for what we're trying to solve with that Navier-Stokes equation, we can use Newton's law of viscosity, which looks something like this, where we have our viscous stress is equal to negative mu times a gradient in velocity. I'll point out that sometimes in some textbooks, they'll switch the letters here, and they might have a negative sign or might leave out the negative sign. That's just convention. And for this problem, it really doesn't matter because we can just set this equal to 0. So this basically tells us that our boundary condition that we're actually going to use to solve the problem, dvx dy, is equal to 0 at y is equal to 0. And so here we have our two boundary conditions. this one right here, and this one up here. So the last thing that I mentioned on that previous slide that we want to figure out is what is this quantity? What is this quantity dp dx? So what is dp dx? And I'll note that this is the dynamic pressure. Our dynamic pressure is equal to this gradient of our standard pressure minus a term that corresponds to gravity, that takes into account gravity. This is rho times g. We know from the situation of our problem that we do have a gravitational component, so now we have to figure out, do we have a pressure component here? To try to understand what this pressure gradient is, let's go back to our picture. Again, we have a solid surface, we have our liquid here, and we also have a gas on the outside, right over here. Now in general, pressure differences within a gas are not going to change too much with height. So the pressure here is probably going to be about the same pressure here on the gas side of this liquid. So we can make an additional assumption, no pressure variations within the gas. And that'll mean that on the other side of this pressure right here in the liquid, we'll have some other pressure. These two pressures have to be equal because they're at the same interface. So that actually means that if we're assuming that there's no pressure variations in the gas, we can also assume that there are no pressure variations in the liquid. So we'll set this equal to 0. And that means that this term in our equation, dp dx, we can set equal to minus rho g. Now we have everything we need to start solving this equation. So rewriting that previous equation we had, we can plug in this term that we solved for earlier. So that's 0 is equal to rho g. And I'm also going to change these partial symbols to ordinary differential symbols, just because we know that there's only a variation of the velocity in the y direction. And now we can solve this using separation of variables by moving all the terms that don't involve the differential into one side of the equation. So I'll start over here, d squared vx dy squared is equal to negative rho g over mu. We can integrate this one time. So we end up with a y over here, and we also have some integration constant. Now at this point in the solving the differential equation, we can actually solve for this first constant c1. It turns out it's a little bit easier to do this now. We know that one of our boundary conditions is that at y is equal to 0, dvx dy is equal to 0. And so we can say, all right away, plug in y to this equation, we get that c1 is equal to 0. So that'll simplify our next step a little bit. We can integrate this equation right here one more time, setting c1 equal to 0 to solve for v sub x. So we get v sub x is equal to rho g over 2 mu times y squared plus a second integration constant. And so now we just need to solve for this last integration constant and we're done with the problem. So again, we have Vx is equal to minus rho g over 2 mu y squared plus c2. And our boundary condition that we have left is that at y is equal to h, our velocity is equal to 0. So we can plug that in. 0 is equal to rho g over 2 mu h squared plus c2. And so this is easy enough to solve. Our c2 is equal to rho g over 2 mu h squared. And now we just have to substitute this in. So we get Vx is equal to this term that we had before, plus our integration constant. This is the solution to the equation, but we can simplify it a little bit more by basically pulling this term out from both terms here. So that gives us rho g over 2 mu times h squared So we can quick check that the boundary conditions still make sense. So again, at y equals h, we should have 0 velocity. If we plug in y equals h to this term here, we get 1 minus 1, which gives us 0. So we do get a 0 velocity at that point. And then we can also figure out where is the maximum velocity in the x direction. So that turns out to be when this term right here, this 1 minus y over h squared term, is at its maximum value, and that is when y is equal to 0. So we see that when y equals 0, which is right when we're at the interface of the liquid and the gas, we get our maximum velocity. So if we go back to this initial picture right here, we can see that when y is equal to 0, which is right at this interface between the liquid and the gas, we're at our maximal velocity. And so we get a velocity profile that looks quadratic from that equation, and also has this maximal velocity right at this interface. I hope you enjoyed this video. Thanks for watching.